All right, let's begin this discussion with where we left off. We are now going to talk about this very simple eigenvalue equation. We're going to use this eigenvalue equation to get us started here. Right, we're going to assume a Hermitian operator A, which we call just an observable. That's an observable. Here it is, the eigenvalue equation. So we know that its eigenkets are given by lambda sub I. Make that little I there a little clearer. And the eigenvalues are given by lambda sub I. So this is a discrete spectrum of eigenkets of the observable A. And then we do the same for the observable B. These eigenkets will be labeled by gamma. So we have lambda is labeled for A and gamma labels B. Now for right now, we are going to assume that these gamma eigenkets are not the same as the lambda eigenkets. They could be, right? A and B could share eigenkets. In fact, they often, that is the case, right? That happens a lot. But for right now, we're going to assume they do not. And the eigenvalues, these are the possible measurements you can make of the observable A and B. And this is clearly the discrete case, right? Now, we have the option of taking any state, any possible physical state, and expressing them in terms of either of these eigenkets systems, either of these collections of eigenkets, because we now know these eigenkets are orthonormal and we presume that they're normalized, right? So because of this, I can write down an arbitrary state psi as the linear superposition of all the eigenkets of the observable A. And this is terrific because once I do this, once I cast psi into these observables, I'm kind of telegraphing to the world, I'm about to make a measurement of this observable. I'm about to measure A. And I've cast it in the terms of the eigenkets of A, and I'm now going to make a measurement. So what are the possible outcomes of the measurement? Well, it's the eigenvalues. So I could get a measurement of outcome of lambda 2, which is a real number, lambda 1, lambda 3, lambda n. And we all know Born's rule that the magnitude squared of the coefficient, A1, A2, that tells us the probability of getting an outcome of lambda 2 in the discrete case. So, great, I can now also say, I could telegraph to the world, no, I'm going to take a measurement of B, right? And I could lay this down. I cast this ket, the same ket. These are the same kets here. And I cast it in terms of a different basis. I kind of screwed this up. This should be a gamma, right? This should be gamma 1 and gamma 2. And now the possible outcomes are gamma 1 or gamma 2 or gamma 3 or gamma n, whereas the possible outcomes were lambda 1, lambda 2, etc. So now I said in the previous lecture, the physics is wrapped up in these observables, right? These observables are the things that we believe are real in the world, and we model those things with these Hermitian operators and their associated eigenvalues. But then I said, but we have to choose. But that kind of is weird. It's like humans are always making models and choosing how to express things mathematically. That's not much of a distinction between classical and quantum physics. So let me remind you exactly what I mean when I say humans have to choose, because I'm using that use of the word humans in a provocative way, right? Like the experimenter, right? So the issue is this, right? And this is intended to be a review of Born's rule, for example. If I cast the system in the state A and I'm telegraphing a measurement, I can execute this measurement. Well, what do the postulates of quantum mechanics say? Well, they say after the measurement, all of these states go away and only one survives. Only one element of the superposition survives. And the state actually collapses into that state. That equality goes away too, by the way. Its psi is dead after the measurement. It's gone. All that's left is the eigenstate lambda 2. And the probability In fact, I should even erase this, right? The probability of that occurring is the magnitude squared of the complex number that is the component of lambda 2, eigenket lambda 2, in the decomposition of psi. Right, that's the probability that we made a measurement of the observable A and received lambda 2, right? That's the Born rule combined with the Copenhagen interpretation of quantum mechanics. Wave function collapse. Now note, I want to be very careful. Wave functions are presumed in the way we're looking at quantum mechanics is called the Schrödinger picture. All the kets are presumed to be functions of time, right? So whenever I write down a ket, I'm really throwing in a t there, and I'm saying, at some fixed time, this is what the state is. And presumably, as time marches on, this state evolves into something different. And I'll say, well, this is the state psi at t now. It's a different state. It's a different state. This psi kind of tells us, well, that's where we started, and it was time evolved, and this is where it is now. So you can link this state to the original state psi by sort of time reversal, perhaps. And that's why it's fair to keep the same psi there. But t is a parameter that tells you how the state changes in time. That's what the Schrödinger equation is. You cannot say that the state psi at t0, and then if you make your measurement at, equals a1 lambda 1 plus a2 lambda 2, etc. You cannot then say, oh, if I made my measurement at t, or at t1, then that suddenly equals lambda 2, right? You cannot do that. You cannot say that this state time evolved itself into this, in the Copenhagen interpretation, right? This act of making the measurement is an abrupt and sudden catastrophic collapse of the state into an eigenstate that has nothing to do with this time evolution process. And we will talk about the time evolution process because we're going to talk about the different pictures of quantum mechanics in a separate prerequisite lesson, because the different quantum mechanical pictures are absolutely essential for understanding QED. The point I'm trying to make is that you cannot think of this changing into this as some sort of time evolution. It isn't. A measurement is an abrupt and sudden catastrophic collapse of this wave function, the superposition of all of these basis states into one of the basis states, and the probability that it lands in any given basis state is given by this modulus squared. This is Born's rule, and this collapse of the wave function, that's the collapse of the wave function. So they're both two separate postulates of quantum mechanics. In fact, let's go check those out. Right, in our lexicon, it's postulate 4 for Born's rule, right? This is, the notation here is in the formalism. That's our next step, is to show how this formalism works. And then this is the collapse, right? So we're dealing with these two postulates. So let me put A2 back in here, but cross it out in red, right? Okay. So now, so we could have done the same thing for B, right? We could have done the same thing. We could have set up our wave function in the basis state B, chosen the B basis. When I say choose the basis B for the vector space, I'm really saying set up for a measurement of B, right? Set up for a measurement of B. This state doesn't care. This state just exists, and it happens to have a projection or a decomposition in the basis state of observable B, and it happens to have a decomposition in the basis state of observable A. This is sort of the coordinate-free version, and once you choose a basis, you kind of put it into a coordinate system. But clearly, the object itself doesn't care about the coordinate system. But when you make a measurement, it suddenly becomes very concerned with its coordinate system, and it collapses to one of those coordinate kets, so to speak. So you could do the same idea here, measure B, and let's say you land on B2 just like before, right? You land on gamma 2. So the probability that happened was the modulus of this coefficient squared, right? So now, let's say you've done this measurement you took the state A and you did this B measurement first. So now you are in gamma 2, right? So you chose to do the B measurement first, and your outcome was gamma 2. So now the question is well, now I want to measure the A observable. Well, you've already collapsed the state to gamma 2, so you're really no longer in the state gamma. So when you measure the A observable, you're measuring the A observable's action on this state, the gamma 2 state, not the psi state. So the results you're going to get is very dependent on how gamma 2 is decomposed into the eigenkets of the A observable, right? This is some other decomposition. C does not equal A. C2, that should be C2. C2 does not equal A2. Cn does not equal An. Absolutely not. And because of that, the chance of getting an outcome, say lambda 2, is now a different number. It's C1 squared. It was before A2 squared. Now it's C1 squared. And besides, it's random anyway. So, did I say C1? All right, this should be a 2. That should have been a 2, right? It's random anyway. So you could have gotten lambda 1 with a probability of C1 squared. So the choice of the order to make a measurement, right? The choice of the order to make a measurement is huge because I'm not guaranteed to get the same result that I would have gotten had I just measured A on gamma. I have different probability distributions, for example, and I may get the same result, but I may not, in fact, get the same result. And this is the part of the human part of things, right? The universe actually cares what order you measure A and B in as far as the answer that is delivered. And what about the universe chooses the order of A and B? Well, it's the human being who's doing the experiment, right? Now, that's a very sketchy way of putting it, right? Because there's plenty of room for the environment to trigger these eigenstate collapses. And there's many, many interpretations of quantum mechanics that really, really dig into this question. But if we're talking about an experimental apparatus, right, where you can choose to measure A first or B, or B first and A, if these basis states are different for the two observables, it cares about what order you make the choice in. A classical system doesn't care. A classical system, this collapse and this probability of landing somewhere, none of that exists in a classical system. So you can measure A first and then B, and A always had a value and B always had a value, and you're going to measure it and you're going to get the same answers no matter how you do it. Quantum mechanics, it's totally, totally different. And, of course, in quantum mechanics is the classic question is, well, wait a minute. What was going on before the measurement, right? Back when I had the state psi, expressed in this basis, right, it's also literally equal to... So, I understand when I make the measurement, I'm going to get some value lambda 1 or lambda 2. I'm going to get some value, or I'm going to, if I measure B, I know I'm going to get gamma 1 or gamma 2, and I know the probabilities for all those things. But what was the value of the observable A just before I made the measurement, right? Was it lambda 1? Was it lambda 2? I know after the measurement it was lambda 2, say, but what was it before the measurement? And of course, this is the legendary fact of quantum mechanics that you are not allowed to ask that question. You're right. There's no determinate value of any measurable before a measurement. And while you're in some state that is a superposition state, right, then the observable A has no determinate value. As long as this state is a superposition state, A has no determinate value. The only way to get a determinate value for the eigenvalue, for the observable A, right? So the only way A could possibly have a value before the measurement is if you know that the state is literally just one of the eigenstates, right? If you know that the state psi is an eigenstate of psi, then you know that it has the value lambda 3. And when you measure it, you will get lambda 3 with the modulus of the eigenvector, which in this case is 1, right? And so the modulus of 1 squared is 1, and the probability, that's the probability of getting lambda 3, which is guaranteed, 1. So, and sometimes that's written down as an actual postulate of quantum mechanics, which is the only way of guaranteeing a certain measurement outcome is to prepare it in a literal eigenstate of the observable. In fact, I think I have this in Griffiths, right? Griffiths writes, Postulate 3, a measurement of the observable Q on a particle in the state psi is certain to return a value lambda if and only if psi is an eigenvector of Q with eigenvalue lambda, right? So that's an example of somebody using this fact as a literal postulate, right? It's not one of our postulates, but it is you can broker this into being a postulate. Okay, so we've reviewed the Born rule, we've reviewed the idea of superposition, and we've shown that, you can blow up a state into two different bases. Let's quickly run through some of the Dirac formalism that helps us through all this and try to make the connection between all of this and the idea of a wave function. All right, so now when we write this down, we know right away what we're talking about. We've got two orthonormal basis systems suitable for expansion in our of any state vector, and it's discrete in its spectrum, right? So we can now, I guess now is a good time as any to address the question of the continuous versions of these issues. So the two classic observables that have continuous eigenvalue spectrum, a continuous spectrum of eigenvalues are position and momentum. Those are the ones we'll do for this definition. So A and B will be some discrete family of observables, and X and P will be the operator versions. And I put a little hat here because I need to distinguish the operator from the eigenvalue. But this is the same thing, right? Funny thing, there's no distinction at this point, except you're missing the index I. Well, that's a distinction. So when you don't have that index I, you have to presume that it is a continuous valued eigenvalue, and therefore there's an uncountable number of these eigenkets. So now we have a kind of a different question on our hands, which is how do we deal with these guys? And the answer is, you deal with them almost the same way as you do here. We will do everything in parallel for both. And what turns out to be discrete sums here simply turns out to be integrals here. But there's a few little beautiful subtleties that really make the difference and give us the connection between this notation and classic wave mechanics. So we're going to work on that right now. To start with, the key reminder is a key point is that the inner product of a discrete eigenvector, discrete eigenvectors is always this delta function. And the inner product of these continuous eigenvectors or eigenkets is the Dirac delta function, right? So that's something important to remember. They're normalized differently. And they just have to be. I mean, you just can't write a discrete, you just can't use this regular delta function. There's no index, right? So you have to use this crazy monstrosity, this distribution of the Dirac delta function to make any kind of normalization. But the fact that X and P have continuous values is really different, because what's going to end up happening is we're going to end up producing functions, and those functions will be wave functions. So let's take a look at how the vector decomposition in these two systems would look. So our classic decomposition of an arbitrary state psi is just this sum over all different i's, sum over all different i's of each of the discrete kets associated with the observable A. Now, what the issue now is that if I replace this with the continuous observable X, each X gets its own component, just like each ket up here gets its own component. Each ket down here gets its own component. The problem is there's an uncountable infinity of these things. So I can no longer discretize them. I have to turn it into a function of x. So the component of the eigenket at position x has to be some function of x. So I know what to put here, right? So right away we have something that is a function of x inside the definition of the decomposition of psi. And this form is always going to be true in one form or another. Well, this expression is the way we write this expression in the continuous case. It's basically like a limit where there's so many of these guys that you just get rid of the sum and you just do an integral. Although that's not a particularly good analogy, actually. But this would be true for any continuous variable or any continuous observable at all. For example, it would be minus infinity to infinity of b of the momentum of all the momentum states integrated over every possible momentum. I'm considering it there's only motion in one line. So, p can be positive, p could be negative, x could be positive or x could be negative, right? But it's continuous variable. So these two are sort of analogous, depending on whether you're dealing with your discrete observable basis or your continuous observable basis. But now what we do is let me just put psi down here in each of these cases. Let's say we want to get at these numbers. I want to know what is this AI and what are these functions here, these two functions of this continuous variable. Well, not a problem. You might think like, oh, it's really hard to figure out what these things would be. But, it's actually super easy. In fact, it's barely an inconvenience to figure this out, right? We just simply calculate the inner product of each of these with the eigenket we're interested in, right? So I guess this would be x in this case, right? Or I guess it would be x prime, and this last one would be p, right? Or p prime. Sorry. So this has to be x prime, right? So we just do this inner product, right? Now what happens on the other side? Well, the other side, it's all linear, and this integration and the sum is just adding, right? So over here, I just throw in delta j or lambda j. Here I put in x prime, and here I put in p prime. And this is no sweat because this becomes the ij delta function, right? So that sum gets wiped out by that ij delta function, and this just turns into delta j. So if I want to figure out what is the ajth component, I just take the inner product with the aj ket and calculate this inner product, and kaboom, I've got it. Likewise over here, when I do this process, let's see, I'm using this in blue now. This is the delta function x prime minus x, and when you integrate over the delta function, that's simply replacing x with x prime. So this ends up being a of x prime, right? And likewise, this is going to be the delta function of p prime minus p, which is going to end up being, after you integrate over the delta function, you're just selecting out the value at p prime. So I now have extracted this function on both sides, right? I've extracted this function because this guy here on the right side, see, it looks like it's a single number, right? It's whatever number I use for p prime. But knowing that this can be chosen to be any momentum and this can be chosen to be any x, these guys are actually functions of x prime and a function of p prime. So I can rename all these things. I probably should have done this with x's and x primes in the beginning, so it lands as a of x, right? But I'm just going to rename it, well, I'll leave it the way it is. X psi equals A of X prime, right? And so there's really no heartburn getting rid of the little prime there, right? And that function, this function here, is given by this inner product. Psi is a fixed state. Psi is a state that we selected from the beginning. That's the sort of subject of our investigation. But I can pick any x, and therefore this guy here is now interpreted as a function of x, right? So given that, this is our connection between wave functions and the Dirac formalism. So the way that connection is drawn is you write psi equals the integral minus infinity to infinity of the ket x dx, and then here you put in the wave function, the wave function psi of x. And this now is the wave function, and it is literally defined as the inner product of x and psi, the bra x with the ket psi. That is the definition of that wave function right there. And in this formalism, the wave function is not a primary object, right? The wave function is just an expansion coefficient of the eigenket x in the case where the eigenket is a continuous eigenfunction, right? When x is a continuous observable. Observable is the word I'm looking for. And because of this, I can actually establish a one-to-one correspondence between state kets and wave functions. If I say I'm in the position representation, in wave mechanics, that means the wave functions are functions of x. So I write the wave function as a function of x. In the position representation, this is literally what that means, right? The ket of the physical state is a superposition of the eigenkets of the position operator, and the coefficient of each of those eigenkets is given by this continuous function of x, which in our formalism really is the inner product of x with psi, right? And this is the connection between wave functions and our formalism. Now, if I was in the momentum representation, that's just saying that the wave function is a function of momentum. And that's not a problem because that was just me saying, oh, the basis kets I'm choosing are psi is the integral from minus infinity to infinity of p times some function a of p. Well, that function a of p, how do we get at it? Well, the way we just did it, sort of roughly speaking, was right here, right? We just got it through this inner product, and we're going to now rename that function just after the actual state itself. We'll call it psi of p, which equals the inner product of p with psi, right? Where this is a continuous eigenfunction. So the position of momentum representation, and when you do elementary quantum mechanics, those are the representations you're in. There are circumstances where you can find yourself in the energy representation as long as energy is a continuous variable. So this is the game we play. But there's one other element of this that we need to look at that's really, really important. Let me rewrite it. So we started with this idea that psi was expressible as a superposition of the eigenkets of the position operator, and each component of those eigenkets was given by this continuous valued function. And then we realized, oh, but that can just be shown to written as x on psi. Whoops, right? On psi, right? That's what we showed over here. We showed that. Actually, that doesn't show it as well as I should. I'll just do it over here, right? Ax is by definition x on psi. When we did the work over there, we landed with ax prime equals x prime on psi, but it's just a relabeling here. So we ended up with this structure, right? This structure here, and we replaced this with the wave function psi of x because we recognized this is just an inner product. It gives you a complex number depending on what x you put in there. You change your x, you get a different complex number. Well, it's a function. It's a complex function of a real variable. That's what this is. That's what the wave function is. It's a complex function of a real variable. And so we replaced it with psi of x. But let's back up a step. Let's not make the wave mechanics replacement, right? Because if we make the wave mechanics replacement, we don't get to see this cool thing that this part here is an operator. We use our associativity of all of this stuff, and we, let me go back to black, we look at it this way, and we see that this operator, this is an operator, right? It's an outer product operator. It is an outer product, and the coefficient of every part of this outer product is 1, right? You know, you could imagine that there's some coefficient for an operator there, but this one doesn't have it, so everybody's got 1. The point is you have psi on this side, right? And you have psi on, and this side is all psi, right? Right? So the only way this whole thing can equal psi is if this operator is equal to the identity operator. And of course, that makes perfect sense because we know that the sum over all of the outer products of all the states, right? We know that that is the identity operator in the discrete case. And this is a very easy to intuit interpretation of the discrete case moved to the continuous case. Instead of the sum, you get the integral, right? So this operator is the identity operator. And it works just like this identity operator would work. Everywhere you can stick I, you can stick this integral. And you can use the linearity to shift things around. So we now have shown the closure relationship. Sometimes you'll see in the literature the following phrase, insert a complete set of states, right? And so what they want you to do is you're looking at something like A inner product B, and they say insert a complete set of states, and then they turn this into A x b like that, with this integral over minus infinity to infinity dx. And that's what they mean by insert a complete set of states, is to throw in this identity thing, which is really writing a identity operator B, right? That's what that's doing. I don't quite know why they say it that way, because this is not a state. It's complete in the sense that the full integral gives you the identity. I guess that's completeness in a sense. But this isn't a ket, right? A ket is what a state is. So I never liked the language insert a complete set of states. But what they mean is throw in this operator I. All right, so now we can sort of summarize where we're at with the formalism. We have the discrete spectrum and the continuous spectrum, and the math is different for both, but quite parallel in many ways, right? So the discrete spectrum, now we're going with the full formalism. So we no longer just write this as some complex number I, right? The full formalism, there is in the Dirac ket notation, there is the symbol for that. Likewise, in the continuous spectrum, you now have an integral over a continuous eigenvalue for some operator that has continuous eigenkets, or a continuous spectrum of eigenvalues. And for every eigenvalue, there is an eigenket, right? And now you have this guy over here, which is still a complex number for a given value of alpha, but we treat this as a function, right? So this is now a function. And associativity gives us the identity operator in this form with the sum on the discrete spectrum side, and this form with the integral. Don't forget this little d alpha. You've got to, you got to integrate over a measure here. Well, you got to integrate over the eigenvalues in the continuous spectrum case. And then to make the connection with wave mechanics, I want to do that. This function here, this is the wave function, right? So you'll see this written in wave mechanics as the alpha representation. I've chosen just sort of a generic continuous variable here, but you need a continuous variable to really have the wave functions that we use in standard quantum mechanics. So there you have it. That becomes the wave function. And now you see that if you ever see this ket referred to as a wave function, it's good and it's bad. It's bad because it literally isn't, right? This ket equals this thing here, which is a superposition of complex numbers and kets, a continuous superposition of all of those things. That's what it is. It just so happens that this function here is a wave function. And there is a one-to-one correspondence between a ket and a wave function in a particular representation, which in this case would be alpha. So because there's a one-to-one correspondence, you can almost say that this is a wave function. And in fact, we can show why that correspondence allows us to very quickly move between these two things. And we'll do that in a moment. But I do want to point out this important fact. We do know, for example, here's a good example of this. In standard quantum mechanics courses, you learn not about eigenkets, but you learn about eigenfunctions. So as an eigenfunction, this might have been presented as phi of, say, lambda I, right? And, or better yet, we would have seen it as just phi of I, right? Just phi of I. X. And we know that, this is an eigenfunction. And there's usually some problem that we've solved, like the infinite square well, the classic problem, right? Infinite square well. And we know that the first eigenfunction of this thing is just sort of your half a sine wave. And then the second, so that would be the eigenfunction of the ground state, which to keep my counting square, I'll say phi 1. But this is the x direction, right? So there's x there. And these are the stationary states, right? So we're not including t, right? We're not including t. And then you might have the second one like that, and then that's phi 2 of x. And these eigenfunctions are wave functions, but they're wave functions for the eigenstates. Well, how do we write the wave function for the eigenstate? Well, if that's an eigenstate, well, we've got this, right? And so the wave function for the eigenstate is just given by this expression, which is just a version of this expression up here. Oh, I didn't include my dx here, right? dx. So it's really no different. I just want to make sure you see that the wave function for the eigenstate is simply this identity operator applied to the ket of the eigenstate, and you end up with this inner product, which is a function over x, and that is the wave function of the eigenstate. And yeah, you could, if you wanted to sort of mix the different formalisms, which really isn't that much of a problem, you just write this as phi of x. As long as you understand that phi are the wave functions of the alpha, are the the eigenfunctions of the alpha observable, the A observable, right? The observable given by the name A and associated with the Hermitian operator A hat, I guess, right? And again, dx. So, all right. So now, what else? What else can we do with this formalism? So the next thing we can obviously talk about is what is the probability of taking a measurement of the observable A and coming back with lambda I. And that probability is axiomatically or by postulate. There's no word postulatically. So I'll say axiomatically, is given by this expression, right? That comes back from this postulate right here. The probability of measuring an eigenvalue an from a discrete spectra is given by this. That's a postulate, right? I don't have to prove why that's the case. That just is the case. So given that that's the case, this expression literally calculated, remember, this is a complex number. If we call that C, this is C conjugate times C, right? That's what, magnitude of C squared equals C conjugate times C. Well, what does C conjugate times C look like? And it looks like psi inner product eigenket I inner product psi, like that, right? And there you have it. Now over here, we can't ask the same question. We have to go back to the postulate and say for a continuous non-degenerate state, we can get the differential of the probability of a measurement of eigenvalue at A to be this square magnitude times the differential of A. So that's kind of a pain. So what does that look like? Well, we go back to our postulates and we write down this. The differential probability is equal to this differential. Now, this wave function, remember this is the wave function in here, its magnitude squared times the differential element gives you the differential amount, well, the probability of finding alpha within a dA alpha range. And remember, this is axiomatic, it's for continuous variables now. So if I want to find the probability of being between alpha, of making a measurement between alpha 0 minus alpha and alpha 0 plus delta alpha, this little delta alpha, I guess this full range is 2 delta alpha. I meant to be just from alpha 0 to alpha 0 plus delta alpha, but I've subtracted a delta alpha and added. So this is like a 2 delta alpha range. Regardless, the chance of making a measurement centered, where the measurement range is centered at alpha 0 and is delta alpha on both sides, right, is this integral. You've got to integrate this wave function. I can call this the wave function. I would have called it an inner product in our formalism, but notice how quickly I drop into the wave function language, because that's the language we all learned it in, and it's actually really efficient. Now, this shows up all the time, and it's kind of a mess. There's a lot of lines, right? So we just call it a wave function now. I did this in the general relativity course too, where I went on in about tensor products and about how authors never include the basis. They do everything with components only, and they never include basis vectors, right? I don't know for those of you who were there for that course, but then the moment I explained it all, I started dropping the basis vectors, because there's a reason for these conventions, right? They're much easier. Anyway, this is the probability of making that measurement between in this range, right? Because you can no longer talk about a continuous measurement very precisely to be one real number value. And you can blow this up, right? This is still a complex function, right? So you can still break it up into its conjugate times its unconjugated parts, right? This is the conjugate of the wave function, and this is the wave function. And that can be written as our classic wave function probability calculation that we learned in elementary quantum mechanics. So there's the link between everything. So this is the probability, I guess I could write it down. This is the probability that the measurement of our value is between alpha plus delta alpha, alpha 0 plus delta alpha, and alpha 0 minus delta alpha, which goes right there. That probability equals this integral, right? Very, very elegant. And yeah, we're going to use the wave function language all the time, but the Dirac formalism is really, really where it goes. It would be hard, for example, to implement the identity operator in the wave function formalism, right? And here you can almost sort of see the identity operator sitting there. The integral's not complete, though. But the point being, the wave function formalism is really good for actually solving the Schrodinger equation, for example. Okay, so what next? Okay, so here's an important one. Let's look at this probability interpretation again. And what do we immediately realize? Well, the probability of measuring in any of the lambda over I, that has to equal 1, which implies that the sum of all of these magnitudes must equal 1. All right, so that's pretty obvious, right? I mean, that's what normalization means. This forces, all the states have to be normalized in such a way that their inner product with themselves is equal to 1. That's really important, or some equivalent to 1. Now, over here, okay, so given that, what's the equivalent on the continuous spectrum side? Well, the integral from minus infinity to infinity, right, of these, these wave functions here, right? This integral over all space, you have to find the particle somewhere, ergo this must equal 1. And this tells us right away that these guys here, right? Well, it's really just one guy, right? It's not two. It's just the wave function, right? The wave function, that must be such that the integral, this integral of the wave function squared, of the magnitude of the wave function squared, which would be the integral from minus infinity to infinity of psi star x, psi of x, must equal 1, right? And what it really means is it must be less than infinity, right? The way to think about this is, given any two wave functions, this integral really needs to be less than infinity. And indeed, it needs to, and if it's less than infinity, it'll be normalizable to 1, right? Some way, you just multiply it by some complex number in such a way that it will end up being 1. But it must be finite to begin with. The point is that in order for this to be true, phi has to be square integrable. And being square integrable, any complex function to be square integrable looks like this. Phi squared is finite, right? Less than infinity. And that restricts the number of possible wave functions that could exist out there. A wave function must be square integrable to make any physical sense at all. And over here, this is reflected by the fact that we don't have wave functions in the discrete case per se, right? We, this term here involves complex numbers. This is a sum of a sum of a series sum of complex numbers, and they have to add up to 1, and they have to certainly be less than infinity in the same vein. So the idea here is that any sequence of complex numbers, C1, C2, C3, Cn forever and ever, some infinite sequence of complex numbers, as long as the sum of that sequence is square integrable, it's a sequence that's eligible to define the components of the components of some wave function, some physical state. So the physical states on the discrete side are just defined by all sequences of complex numbers that are whose sum is finite, right? And in principle, all the squares of these guys, right? Well, they need to be normalized such that all of those sums, the sum of all this thing limits to 1, right? It limits to 1. On the continuous side, the statement is that the wave function, which is really this in the bracket formalism, must be square integrable. And if it's not, then it can't represent a physical state. Just as a sequence of complex numbers that diverges in their sum cannot represent a physical state. of a discrete spectrum. Notice that the divergence has to be in the sum of these squares. The sequence itself must obviously not diverge either, right? But the sum is what we're interested in. So there's two ways. So here we're interested in a space of all possible sequences that don't, whose sum converges. And here we're interested in a space of all possible functions, right? So this is what we usually, when authors refer to the Hilbert space, right? The Hilbert space L2, they're referring to the Hilbert space of all square integrable functions that satisfy this. So that's why when we go to Griffith's first postulate, his version of it, now I think we can understand it. The state of a particle is represented by a normalized vector, which he presents as a ket, in the Hilbert space L2. Well, that's a problem, of course, because the Hilbert space L2 is functions of x that are square integrable, but a ket isn't square integrable. But what he's really doing is he's just taking full advantage of the obvious fact that there's a one-to-one correspondence between these kets and these wave functions, right? And so you can kind of get away with saying that in quantum mechanics. That's really not so bad. For example, say I was interested in the inner product of the wave function, well, I'm getting ahead of myself. The inner product of the state phi with the state psi. I know I'm going to screw this up. This is phi and this is psi, right? So in wave mechanics, this is the overlap of these two wave functions. That's what that's called. And the calculation is this integral, right? I take the wave function of the state psi, its conjugate, integrate over all the real line against the wave function of the state phi over the real line. Well, all right, so this is the wave function form for the inner product. This is the Dirac Formalism form, and the connection is through the identity, right? I'm going to throw in a complete set of states, to use the language that I don't like. So again, now I integrate over all the real numbers. Here's psi. Here's my x. Here's my x. So there's the complete set of states, so to speak. And dx, right? And by definition, what is this? Well, this is phi of x, and this is psi of x bar, right? So there's the integral, there's dx, it's over the reals, perfect match. And that is the kind of thing you have to be thinking about, right? And actually, you see, this is a little bulky compared to this, right? I mean, is it really? I mean, you could do without the x's here. If it's really implied that they're functions of x's, so if you really want to do this clean, you get rid of that, and you just write. Let's see, what do? You write psi phi dx, and you know that psi and phi are functions of the variable there, the variable of integration. On the other hand, you still got an integral. I mean, this is obviously the cleanest, right? This little thing right here. But the connection is the connection, right? I mean, you would probably not write this. If you were using the Dirac formula, you would just work with that. Okay, so this gives me reason to forgive, right? If I just set this up like this, then I would be saying that's the wave function psi and the wave function phi, and you can make this translation so easy that the distinction becomes very blurred, and that's the way I think Griffiths went with his work. All right, so now I don't want to stop this lecture until I've covered this last topic, and then we'll stop. But this guy right here, it seems so easy, right? Because you just talk about the square integral functions, and you know you've normalized the state psi. The problem is when we apply this rule to the eigenkets of our continuous operator. In this case, I guess I wrote it down as position here. I've been using alpha here, so I suppose I should use alpha here, right? This should be alpha alpha. But let's now think about the position operator, right? The position operator acting on position eigenkets gives you position and returns the ket, right? So there it is. There's the position operator. The problem is that we've normalized these guys with the delta function. And so I have x prime, x double prime is literally equal to x prime minus x double prime. So now, what is the probability of measuring the eigenvalue x? Now, this is a weird question, right? Because I've already kind of gone through this explanation that you can never really measure a continuous variable precisely, right? The problem is that it is still an eigenvalue, right? And what we're going to discover is that the probability of measuring an eigenvalue x is still going to be an integral over the real numbers. All right, so before I go, I want to make sure we cover this last important topic here. Let's take a look at this continuous spectrum case up here, right, where any state psi is expressible in a continuous basis with a wave function tacked on. So let's apply that logic to the state ket x itself, right? So if you just replace psi up here with the position eigenket, and we choose as our basis states the position eigenbasis, right? So this here, right, is the identity, right? This part right here is just our identity. So we've inserted a complete, we've basically done the identity operation right there, and that's the right-hand side of this. So now we look at that and we say, okay, I'm going to do the most obvious thing in the world. I'm going to calculate the projection of the state onto itself, which should be 1, right? In fact, that's what this is up here, right? If I just replace alpha with x prime and psi with x, right, we get this statement that this thing should be 1, right? That's what being square integrable means for the wave function. So I need to squeeze in the x over here. The problem is now, if I look at this, this is normalized using the delta function. Right? So I know that this guy is x prime minus x, and I know that this guy is delta x minus x prime, right? The problem is that when I execute this integral, I can execute it over one of these delta functions. The bottom line is you force x prime to equal x, right? And what happens is you end up with the integral of delta of 0. Or actually, no, you don't end up with the integral of delta of 0. You end up with just delta of 0, right? And this delta of 0 is infinity, right? So this guy is not actually square integrable. It's a state ket of the it's a state eigenket of the position observable, but it's not square integrable. And this means that the literal ket x is not a physical state. And this will be true for all of the continuous kets. The ket of the momentum basis, not a physical state. And the reason this is important is because we still use it as a basis for our truly physical states, despite that it itself is not a physical state. So you could actually argue that if V is the vector space of all physical states, right? How we have V, the complex V. If I choose a basis of a continuous operator, an operator with a continuous spectrum, then the basis is arguably not really in the vector space. And that is super weird, right? You don't have in any normal vector linear algebra a situation where your basis vectors are not themselves vectors. It just doesn't make sense. Remember, the addition rule that you use in this sum, right? If you were to break this sum up into a dense integral, right, the sum would be the vector sum. That's the only way you can do this. So that is the soft spot of all of the mathematics here. And it was wrestled with for a long time, and people struggled with this. And this is the thing that Dirac did that was considered utter madness by mathematicians, right? Utter madness. Now, since then, mathematicians have come around and created a whole body of mathematics to cover this case. And it's pretty esoteric stuff, right? It's called, the subject involves terms like Gelfand triples and the rigged Hilbert space, which you can imagine is some kind of sort of extension of a Hilbert space that includes things like this that are not actually part of the vector space, right? Remember, the vector space should be the space of all physical states, and this is not a physical state. Now, as a matter of practical interest, you have to, it forced physicists to think about, well, can you ever really measure a position with infinite levels of precision? And the answer is like, well, obviously not, right? There's no instrument that could do this. And it turns out even in principle, it cannot be done. So what's important to understand is if you write a state psi as a sum over the real numbers in this way, and you make a measurement, you're not collapsing, in this case, to a specific position ket. You don't collapse to a specific position ket. You can only collapse to a state that is in some range, right? Some range and has its own wave function, right? Some new wave function. I'll call it beta, right? Oops, I don't need to struggle here. You're going to collapse into just the range that your equipment can actually measure. So you always collapse into a state of this nature. And this is sort of a really advanced topic, but the point that you have to understand is you will frequently see how references to the fact that continuous, the eigenstates, the eigenkets of continuous operators with a continuous spectrum, they're not actually physical states at all. However, we kind of treat them just as though they were, right? And all of the rules that we created over here, these are the rules that the formalism guides us in, right? So the formalism doesn't worry too much about this. But physicists and mathematicians certainly do and have a great deal. The only book that I've got that actually treats this question, and I'll write it down for you, is this book, Quantum Mechanics, Foundations and Applications by Arno Bohm. And it's a slog, let me tell you. It's a real slog. I gotta say, unless you're really interested in this, it's not really worth your time. However, Griffith speaks about this in detail, but no more detail than I just did, really, except that he exercises it for the momentum states as well. And we will do that, but we'll do it in a different series of lectures where we start talking about how some of these, about unitary operators and how the development of the Schrödinger equation. I think we should do that, but it won't be in this formalism lecture. But the point is the formalism is really interesting in the sense that it works great, but it's got this weird little problem that ultimately I think most people feel is fixed, so fair enough. And the formalism definitely works, so we know that everything's good. But we got to remember, it's not possible to measure a position or any continuous variable with infinite precision. So you can never collapse into a physical eigenstate that is specified by an infinitely precise real number. Now, you could actually argue that, well, maybe our problem is using real numbers at all, right? You could say maybe this whole thing needs to be readjusted where you can only use a certain limited number of states. And that is a solution, right? If your system is, a few particles, you could enclose it in a really big box. And that really big box would restrict the possible places a particle could ever be, right? Because you suddenly don't have minus infinity to infinity anymore. You have minus L to L. And that can actually be turned into a discrete spectrum. So what you end up doing is instead of having a continuous spectrum of values of position, now you have a very dense discrete spectrum, right? Very, very dense discrete spectrum. And you insist that the particle be in one of the eigenstates of this very, very dense discrete spectrum. And you can even go so far as to say it's so dense I'm going to have trouble keeping track of it, so I'm just going to keep track of the density of states, right? And you can start introducing things like that. But in the end, if this discrete spectrum goes to infinity, right, then you're in trouble because you're going to get a continuous set you're going to get a continuous spectrum, and you're going to get each one of those continuous spectral possibilities will get its own eigenket, and you'll be back in the same situation. Now, it's also true that there was a problem for momentum, right? Because momentum if you start integrating momentum from minus infinity to infinity, what the hell's that? That's infinitely fast particles, right? That's not a possibility. That violates that you can't even get close to infinity, right? You have trouble when you approach the speed of light, right? When the momentum gets to be such that the kinetic energy, the particle gets near its rest energy, right? m0c squared, then non-relativistic quantum mechanics completely breaks down. So you could argue that this problem of this infinitude, this uncountable infinitude of states goes away because this whole mess doesn't even work when you get down to localizations that are so tight that momentum becomes so unpredictably high that you start violating relativity with a large fraction of a high probability. And but that has a lot more to do with the relationship between position and momentum, which we're not covering in detail in this formalism class. This was just about the formalism. But that's a really important point, right, is you have this interesting problem that your continuous spectrums have eigenkets that are not really physically realizable states. But don't dwell on it too much unless you're interested in it, in which case, more power to you, and dwell on it all you want. Somebody's got to think about these things, right? So, but these rules are still the rules that will guide you through this entire mess. And notice the real physical states, they are in fact square integrable, right? You're dealing with wave functions that are square integrable. Okay, wow, that was a long lecture. Sorry. Break it into two, take it easy, and we will now move into another topic eventually here when I find some time. Thank you.